Okay, let's see. Announcements. I think I had a couple. Trying to remember here. Yeah, I had a couple. So if we go to the Sakai site, where I have the syllabus listed, I have a few other items there. First off is the PDFs of the Lesson 1 homework and the ebook notes. If some of you are still waiting for your WebAssign access cards to arrive, last time you asked me to copy the homework 1 anyway, into a PDF, and so that's listed here. Of course, you can't submit your answers, but you can start working on the questions and figuring them out, and then when you have your access, you can submit them. So that is posted there. Also, the ebook. We were running into this problem where if you hadn't paid for your access yet, you could see the homework, you can see the announcement area, but you could not look at the ebook, which again is not really a book. It's just a collection of notes. WebAssign calls it an ebook. So I said I would grab those notes and put those in a PDF, and those are here. This is like a short version, not broken down into subsections, but it gives the reading assignment for the entire lesson, then all of the key math notes and exercises for the entire lesson all at once. Though I reported this to WebAssign, I reported to them last year as well, but I think they might have fixed it this year. So if you're having a problem, if you haven't paid yet or typed in your access code, check and see if you can get into the ebook. If you still can't, let me know. That means they haven't fixed it. But I think it's been fixed, and you have that ebook access even before payment. Any questions about any of that stuff?
Can you say again where that link to that ebook is?
So the link to this kind of temporary PDF is in Sakai, but the actual link in the actual ebook is in WebAssign.
Thank you.
It's in like 2 or 3 locations. It's on the top bar in WebAssign, lower right beneath the announcement area, and we link to it at the top of every homework as well. And that's where the reading assignment is too. Okay, so let's dive back in. And last time, I think we left off talking about circumpolar stars. And I still had a little bit of material there for you. Just a reminder, circumpolar stars are stars that never rise or never set. They're always down or always up. We were looking at this figure last time. This is someone standing at a latitude similar to North Carolina's latitude. They're clearly in Africa or Europe, but if you spin the globe around, it's probably not too far off from North Carolina's latitude. And you can see here we have an extension of our rotation axis. And these diagrams are a little bit hard to visualize because it's 3 dimensions being plotted on a 2-dimensional surface. For the rotation axis, just take a look at the north-south line and imagine tilting it up. So this is in line with the north-south line tilted up. It's not like halfway between north and west. Anyway, you go over towards the north, you go up, and that is the celestial pole, right along our rotation axis. And then down here you have the south celestial pole. And so you have a grouping of stars that never set. They're going in small circles around the north celestial pole, and another grouping of stars going in small circles around the south celestial pole, so they never rise. Anything else will rise and set. Okay, so these are circumpolar stars. And let me ask you a couple questions and just shout out answers. Even with a lot of students, I think I can discern the various answers. So the first question is, if we go up to the North Pole of Earth, standing on the North Pole, what fraction of the stars are circumpolar? Standing on the North Pole, what fraction are circumpolar?
Half. Should be half, right?
Half is, I appreciate the boldness of the first answer, but no, it's not half.
Is it
1/4?
All of them are circumpolar?
All of them?
It's all of them. Yep, that's right, it's all of them. So let's think that through here. So if we, all of them. So if we are standing on the North Pole, the North Celestial Pole is directly overhead. In fact, I have a figure back here. If we're standing on the North Pole, the North Celestial Pole is directly overhead, and everything is going around it. And we, in reality, Earth is spinning on its axis, but from our point of view, the celestial sphere is rotating on this same axis. So the stars up by the North Pole go around it here. The ones a little bit farther down go around it like that. The ones close to the equator go around it like that, always above the horizon. So here's a figure from the textbook. We know we're at the North Pole because of the polar bear. If we look off towards the horizon, the stars will be going horizontally, not rising or setting. Everything is going in a circle around that point. Since that point's directly overhead, everything's going around in the plane. Okay, and here's a nice figure that illustrates this. Let me make this bigger so you can all see it behind the faces. So this is a picture. It's a all sky camera, so you're looking at the entire sky. And was this taken at the North Pole or the South Pole? You can actually tell in two ways.
North Pole.
It's not the North, it's the South. So here are the two hints. The first one's astronomical. We know that there is a bright star near the North Celestial Pole. If we look here at the Celestial Pole, there's no bright star. That means we're in the Southern Hemisphere. There is no bright star, no Polaris in the Southern Hemisphere. The other way you can tell is the structures here. The North Pole of Earth, there's nothing. But the South Pole, there's a scientific research station. All sorts of experiments, scientific experiments, maybe some military stuff. Telescopes are there as well. And it's a wild environment to work in. When I was a graduate student, I was invited to go down and work at the South Pole, but the deal was I would have to do winter over. And there are like two trips you can make to the South Pole, a 2-week visit, which I would jump at, that'd be awesome. And the other is winter over. And they're always desperate for scientists to go do winter over because it's it's months and months of darkness and cold and depressing. So I did not go. Anyway, you can see that we're at that station. So South Pole, and if you look at the star trails, this is 24 hours. So this was taken in winter, not our winter up here in the north, but their winter down in the south. And at the South Pole in winter, it's dark all the time. And so you can have a 24-hour exposure, and you can see the stars going around the celestial pole, none of them crossing the horizon, nothing rising, nothing setting, so all circumpolar. Okay, let me ask the flipped version of this question, and that is if you're on the equator, what fraction of the stars are circumpolar?
None.
None. Yep, that's correct. Let me grab my globe here. Okay, so if we're standing on the equator of the globe, maybe I'll find a land mass, so we're not standing in the ocean there. Of course, the person here is not to scale. They're really, really small. So from that person's perspective, this is the ground. You can imagine just extending out. And north is in this direction, south is in that direction. So the North Celestial Pole will be on that person's horizon towards the north, and the South Celestial Pole will be on the horizon towards the south. And all these circles go around the celestial poles, but the poles are on the horizon. That means half the circles above, half the circles below. So you have to rise, you have to set. If it's like the North Celestial Pole is over in that direction, for our fictitious orientation of the room that we agreed upon last time, north is this way, south is that way. Imagine little circles. It'd pop up, it would go over the pole, and then it would set below the horizon. Same with something rising over there. It does a long journey, but it sets. If it rises due east, sets due west. Going over to the south, a little loop around the pole as well. So everything rises, everything sets. If you're on the equator, things will appear to rise straight up, and then they'll move over and set straight down. So no stars are circumpolar at the equator. Okay, good. Okay, This is the last thing for motion of the celestial sphere. This is an exercise that I want you to do, and it's written in the ebook. So let's go over to the ebook here, and we are under lesson 1. Go down to motion of the celestial sphere. Down near the bottom you have exercises, and as I mentioned last time, a lot of these links are dead. The UNL applications don't work anymore, and don't worry about that. But if there's an exercise that's really important, I'll mention it, and this is one that I want you to do. And it's written here in a paragraph form. On a clear night, I want you to go out and sketch the northern sky and the southern sky, and then come back a few hours later and sketch it again. We've spent some time talking about the motions. You probably understand them intellectually, but there's nothing like actually going out and seeing it with your own eyes and making it become real in your mind instead of just an academic exercise or thought. So the way to do this is go out maybe early in the evening when it's just gotten dark enough that you can see some stars. It works best if the moon is down or not very bright. And towards the north, start by drawing some reference points, like if there are buildings and trees, draw them, and then draw the bright stars. You don't have to draw every star in the sky, but bright stars, you can even connect them. You can make your own constellations. And then do the same in the southern sky. And then come back a few hours later and do it again to notice the motions. Because when you look out the sky, you see stars up there, but you don't often notice the motions. You know, maybe you do this on a Friday night where, you know, you're going out to have some fun. Of course, we're in the age of COVID, so no one gets to have fun anymore. But if it wasn't for COVID, maybe Friday night, you go out, you do your sketches, you go out, have a fun evening, you come back and then do the sketches again. Of course, depending on the type of fun you were having, your second set of sketches might be blurry, but that aside, you'll notice the motion of the stars, and it should be different in the north versus the south. Because in the north, we can see the north celestial pole and everything moves around it. So the stars you draw, the constellations, the ways you connect the dots, you'll see this pattern rotate on the sky around the north celestial pole. Actually, it goes around this way. Now in the south, everything's going around the south celestial pole. That pole is below ground. You can only see it down in the southern hemisphere. So we're seeing stuff in the outskirts of that circle. Things will be doing broad swaths from the east to the west. It's going to be more east-west motion than rotational motion. So make your drawings and see if you can see these effects. It makes it real in your mind. I'm not asking you to turn the drawings in. For these exercises, you don't have to turn things in, but on the next exam, I will ask you about these things, at least some of them. So it helps if you actually go and do the exercise. Plus, it's fun to just actually look at the sky a little bit as part of an astronomy course. Okay, any questions about motion of the celestial sphere? All right, so the next thing I like to do is just a little pause, because we're now, we've talked about the motion of the Earth, at least its spin on its axis. Now we're going to throw the sun in there, and we're going to throw the moon in there, and talk about the relative motions between pairs of them and between all three of them. And this figure is from a couple lectures from now, where we'll be talking about eclipses. This is a solar eclipse. But the thing about all these figures, they're trying to get a concept across. And to do it, they can't draw anything to scale. Like, the scale is totally wrong. Here we see Earth is almost as big as the sun, and the moon is like 1/3 the distance between them, and none of that's right. But if they were to draw it to scale, you'd barely be able to see the sun, and the Earth and moon, you wouldn't be able to see at all. They'd be smaller than a pixel at the proper distance, given the relative sizes. So these are conceptual drawings, and the scale is all wrong. But after looking at a bunch of these, you may walk away thinking this is the scale of things out there. So what I would normally do is I would do a scale model of the Earth, Moon, and Sun system in class. We'd just build one. That's too hard to do online. I don't have enough space in this room or volunteers or anything like that to help me with 2 ends of the tape measure. So I'm just going to describe it and show you a picture of what it looks like. So let me go to the dot cam here. And we'll come back and we'll look at this in a little bit, the warm-up question. But in the scale model, I use this for the sun. So we have a 4-pound weight ball, and the sun is this big. Well, how big is the Earth compared to the sun? We calculated that in the previous class, or a couple classes ago. The Earth is what fraction the size of the sun? Do you remember?
100th?
100th, yep. And so that's about a millimeter on this scale. So Earth is about that big, and the moon is about 1/4 the size of the Earth. And given the scale of these things, I need to put the moon about 1 inch away. So that's the moon. So those are the relative sizes of the objects, and this is the correct scale. Although that's hard to see, I can put up a little diagram here. This is the Earth-Moon system. Let me shrink it a little bit, because I know for those of you on a single monitor, my face is, and a number of your faces are over on the right, and so that would block the moon there. So here we have Earth, Moon. This is to scale in this particular diagram. And so this is the little mini version of that. Now, for the sun to be to scale, we have to move it, and you move it 38.5 feet away. And I have a picture of what that looks like. So here's one student down at the front of my usual classroom. This is where we would have been this semester. He's holding the Earth and the moon, little like a ball bearing and a fragment of chalk dust, 1 inch apart. And then I'm 38.5 feet away, and I have another student behind me in this picture, you can't see her, holding the sun. And the point is, the solar system, this is just the inner solar system, but the solar system is mostly empty space. It's actually very similar to atoms. Atoms are also, as we'll learn later, mostly empty space. The universe on all scales is mostly empty space. Between stars, mostly empty space. So anyway, you're going to look at a lot of these diagrams. Just keep this in mind, that this is the actual scale and configuration of things. Okay. So the next topic, we're going to throw the sun in here, and let's approach it from the standpoint of time. So the topic will be astronomical time. Now we measure time, and there are a couple different ways that you can measure time. Everybody in their everyday life, they use what we call solar time. You know, watches, clocks, they're all synchronized to the motion of the sun. That's because we like to wake up in the morning when the sun's coming up, have our awake period illuminated by the sun, and we go to sleep afterwards. Not everyone, some people work the night shift, but in general, civilization works with sun up, sun down. So solar time, let me grab the right page of notes here. So solar time, let's define the solar day. You know, one solar day, we can break it up into 24 solar hours. You can break those up into minutes and everything. But technically what this is, it's the amount of time it takes for the sun to go completely around the sky. Either from rising on the eastern horizon, going all the way around and rising again, or from setting on the western horizon, going all the way around and setting again, or the meridian. And that's a term that I want you to know. So imagine the great circle beginning due north, going overhead through the point directly overhead, which is called what?
Zenith.
Zenith, and then going all the way due south. So one giant arc cutting the sky into two parts. Maybe I'll draw it here. Here's the horizon with east over here, west over there, north, south. Imagine this great arc in the sky. This is zenith up here. Eastern sky on one side, western sky on the other. So this arc is something that we call the meridian. So imagine the sun crossing the meridian, kind of around midday. It may not cross directly overhead. It crosses somewhere on the meridian. The sun doesn't always pass directly overhead, as we'll learn. And then the amount of time to go completely around, set, rise again, and come across the finish line, that is one solar day, 24 solar hours. Okay. Now, that's great for things tied to the sun, but almost everything else in the universe, sidereal time is a better measure. So let's define one sidereal day. The term sidereal, what does that refer to? What kind of astronomical object? Sidereal means?
Star.
Star. So this is the star day. It's the same idea. How long does it take for a star on the meridian to go completely around, set, rise again, and hit the meridian? So it's one sidereal day. We can call that 24 sidereal hours. Break it apart into 24 sidereal hours. But if you convert that to solar time, it's actually 2356 solar hours and minutes. So there's a 4-minute difference. The sidereal day is shorter, means the solar day is longer by 4 minutes. So why is that? Why is the solar day longer? Why does it take 4 minutes extra for the sun to get back in position? Anyone want to venture a guess?
Because the Earth also rotates around the sun, so in order to make one full revolution, it has to make up that extra distance.
Yes, exactly. Except, and I'm glad you used both terms, rotation and revolution. I think you had them backwards.
Okay.
But that's great because that's the next thing. I want to define these terms. I often get them mixed up too. So rotation and revolution. Rotation is the same thing as spin. That's spin on the axis. Earth spins once a day, it rotates once a day. The word revolution is referring to the orbit. We revolve around the sun. We don't rotate around the sun, though it's common to say it that way, and I'll make the mistake as well. So orbit is revolution, spin is rotation, and the sidereal day is totally connected to the spin on our axis. How long does it take to spin completely around on our axis once? The solar day is connected to both of these. Yes, we're spinning on our axis, but we're also moving in our orbit. And so we're at a different position. If we want to get the sun back into the same part of the sky relative to us, since we moved, we have to rotate extra. I know that sounded confusing, but I have a few diagrams to bring that home. Let me see. Where are my diagrams? Right here. Maybe it's this one. Yeah. Yep. Okay, so here we have, let's start at this particular time. We have Earth, we have someone standing on Earth at point A. The sun is overhead. Maybe it's not directly overhead, but let's say it's on the meridian. And then if you keep going beyond the sun, way, way off to the left, there'll be stars. We can't see them because it's daytime, but they're there. Now, after one sidereal day, Earth has done a complete rotation on its axis and is pointed back in the same direction. It's not pointed at the sun anymore because we've moved in our orbit, but let's come back to that in just a second. We've done one full rotation, pointed in the same direction, and I argue that we're pointed at the same stars that we were before. You may say, well, wait a minute, we've shifted up. So we're actually not pointed at the stars behind the sun, we're pointing at the stars a little bit higher up. But the stars are so, so far away, it's a minuscule difference. And let me draw something to illustrate that. I'll kind of draw, let me get the dot cam up front here. So let's come way over here maybe. There's the sun, there's the Earth, here's the Earth one day later. None of this is to scale, of course. So here's that person looking at the sun. And one day later, if you want to look at the sun, you'd have to look in a different angle. But imagine instead of the sun, some distant star. I'll draw it over here. And here's the line between Earth and that distant star on day one. Here's the line between Earth and that distant star on day two. A little bit wobbly, but you get the idea. And these lines are certainly not parallel, but these lines are much closer to parallel. They're not technically parallel, but pretty close. Now, if I take the star and move it farther away, the farther away I move it, the closer they are to parallel. If this is the distance between the sun and the earth, the closest star to us would be about 2 kilometers in that direction. And so if you imagine pulling this 2 kilometers out, these two lines are almost perfectly parallel. And that's why you can say after one sidereal day, we're pointed back to the same stars. Make sense? Okay. But we're not pointed to the sun. So if we want to point to the sun, we're going to have to rotate this little extra bit. And we want to know how long it takes. How much of a rotation is that? And how long does it take? So let's calculate that. Let's do a little bit of math right here. 2 parts of this calculation. First, let's calculate this angle right here. After 1 day, we've moved in our orbit, and it says we've moved almost a degree. So let's see if that's correct. Put the dot cam back up. Okay, so theta is a good symbol for angles. It's a generic symbol for angles. What angle have we moved in our revolution around the sun? Well, you always start with what you know. So 1 day later. And so what motion are we talking about? It's the motion around the sun. In 1 day, we're trying to figure out how many degrees do we travel. So let's think about the full loop. To do 360 degrees around the sun takes how many days?
365.
65. Yeah, 365 days to do 360 degrees. 1 year to go around the sun. So when you're trying to figure these things out, and we've had a couple examples now, warm-up questions where you're doing this, it really is unit conversion. You just have to think about what motion am I talking about. For this particular thing, we're asking how far did we go in our orbit. So it's the orbital motion, 365 days and 360 degrees. And second, we'll see using the rotational motion. Anyway, 360 and 365 are almost the same. So 1 times 360 divided by 365 gives you that 0.98, what was it? 6, 0.986. The days cancel, so you're in degrees. So each day we travel about 1 degree of our orbit around the sun. So here we are, but we're going to have to then rotate on our axis an extra degree to get the sun back on the meridian. You may remember from high school geometry, if you have 2 parallel lines, here and here, and a line bisecting both of them, this angle here is the same as this angle here. In other words, if we move 1 degree up in this direction, if we revolve, orbit 1 degree in this direction, we're going to have to rotate, spin 1 degree farther to compensate for it. So let's calculate how long that would take. So change in time. Delta means change. We'll use it a couple times in this course, so I'll just throw that there. The change in time, again, you start with what you know. How long does it take for Earth to spin on its axis 1 degree? Well, to spin 360 degrees on our axis takes how many hours? No one wants to answer the simple
24.
24, yep. 24 hours. And we know in 1 hour we have 60 minutes. Degrees, hours cancel. The answer will be in minutes. 60 goes into 360 how many times?
6.
6, yep. Cross that off, 6. 6 goes into 24 how many times?
4.
4 minutes, and those are the 4 minutes that we were looking for. The sidereal day is 4 minutes shorter, and the solar day is 4 minutes longer because of this extra rotation that we have to do on our axis. Okay, let me see what's next. Well, let's think about the implications for that. Yes, the solar day is 4 minutes longer. That means the sidereal day is 4 minutes shorter. That means stars will hit their places 4 minutes earlier every day. The sidereal day is 4 minutes shorter. So according to our solar clocks, things will rise 4 minutes earlier. They'll set 4 minutes earlier. They'll cross the meridian 4 minutes earlier. Suppose a constellation is setting at 9 p.m. The next day, it will set at 8:56 p.m. Next day it will set at 8:52, and day after day, earlier and earlier, until it's then setting in the daytime sky. The constellations at night will move into the daytime sky, and the constellations that were in the day will move into the nighttime sky. And this is why the constellations change with season. I don't know if it's something that you personally noticed, or maybe you knew just academically, but it's something you should probably keep an eye out for. And let me give you a couple pointers there. So this is the summer sky. These are some of the constellations. If you're looking south during summer, you see these constellations. And 3 of these stars are a lot brighter than the rest. It makes them easier to see. It's Deneb, Vega, and Altair. They form a triangle. So if you go out in summer, we're at the tail end of summer, so this would be early in the night. You can see these still. You'll see what's called the summer triangle. If you go up to the short side of the summer triangle, focus on Deneb, you can also see the constellation Cygnus. Sometimes it's called the Northern Cross. Sometimes it's called Cygnus the Swan, where this would be the head of the swan. These are the wings. That's the tail. Anyway, something you can see, but it's going to set 4 minutes earlier every night until eventually it's in the daytime sky. And then the winter constellations replace it. And as we work our way through the semester, you'll see these more and more. Late in the night, but moving earlier each day. The most familiar one is, of course, Orion, which we talked about before with the belt and the sword. And just tailing Orion is Sirius. You may not see the whole constellation, but Sirius the star is the brightest star in the sky. That's the hunter's dog following him. So just certain things to look out for, and you'll notice that they move earlier and earlier every day and then shift from season to season. Okay, before we get to this, let's go back to the warm-up question and see how you did. So let me put it up on the doc cam. Let's see, I'm gonna slide this over here. Take a look at your answers, bring up the doc cam. Okay. So a constellation rises at 6 a.m. near the end of the night. How many months until it rises at midnight, near the middle of the night? So how many months? So this is a little trickier than yesterday's because it's kind of a two-step process. And we have 34 responses, and I think we have, I'm counting you right now, at least 75 of you. So I'm going to give you a minute or so to work this through. Give it a go. Maybe 60 seconds. Maybe another 20 seconds. Okay, you can keep submitting, but let's take a look at what we have. Okay, looking at the values there, I see a lot of the correct answer. Look at the histogram. Maybe add some bins here. Yeah, so most of you got the right answer. 3 months is the right answer. So let's work through that calculation. And there are 2 ways that you can go about doing this here. Okay, so start with what we know. It's rising 6 hours earlier. 6 hours. And let's convert this to minutes. So in 1 hour, we have 60 minutes. So rising 6 hours earlier corresponds to rising 6 times 60 is 360 minutes earlier. And we know it's 4 minutes per day. The stars, the constellations, they rise 4 minutes earlier per day. The question is, how many 4-minute intervals do we have in 360 minutes? So again, start with what we know, 360 minutes. Every 4 minutes corresponds to 1 day. And it asks for it in months, so every 30 days, roughly, is 1 month. Cross out the minutes, cross out the days, the answer would be in months. And 360 divided by 4 divided by 30 is 3 months. So that's one way you can do it, using the fact that everything rises 4 minutes earlier each day. The other way you can do it is to actually use the 2 physical motions. Basically do the steps we just did, but backwards. So let me show you that. 6 hours. And so let's start with Earth's rotation. How long, in 6 hours, through how many degrees does Earth rotate? Well, Earth does 360 degrees in 24 hours. And so this means, that's why we use bracket notation. I got it backwards there. I can't cancel out my units. 360 degrees in 24 hours. Good. I know I did it right this time because my units cancel. So 6 times 360 divided by 24 is 90 degrees. So in 6 hours, Earth spins 90 degrees on its axis. And the question is, how long does it take for Earth to go 90 degrees in its orbit around the sun? Remember, these 2 motions are canceling each other out. We orbit for a certain amount, and then the Earth has to rotate that same amount. So if we had to rotate 90 degrees, that means we orbited 90 degrees, and Earth goes around 360 degrees around the sun every 12 months. So 90 times 12 divided by 360 is 3 months, where the degrees and degrees cancel. So 2 ways you can do it. You can make use of the fact that we know it's 4 minutes earlier per day, or you can build in the 2 actual counteracting motions, rotations and revolutions. Make sense? Well, it's good. We're recording, so if you need some time to look at it, you can go back and look at the calculation a little bit more carefully. Okay, let's wrap up astronomical time and then just briefly start the next section. So the last bit here with astronomical time, and we're talking about how the constellations change with season, and this connects to astrology. Now, astrology and astronomy are different. Astronomy is science. You're in an astronomy course. I always have that one student at the end of the semester emails me because they're not doing well in Astrology 101. And I think there's a correlation why they're not doing well, because they think it's astrology. Astrology is horoscopes and silliness like that. And but let me explain how the constellations of the zodiac work. We all know our sign. The celestial sphere is full of constellations, but from our point of view, the sun moves through the celestial sphere and will block a cycle of them. And in reality, the sun is stationary and Earth's going around. So like I was born in January. So Earth would be right here in its orbit. And in January, the sun is blocking the constellation Capricornus. That means I'm a Capricorn. So just whatever constellation in this cycle that the sun is blocking when you were born is your sign. And then, the rest of astrology is, a lot of these horoscopes, just to be honest, It's English majors that have graduated from college but don't have their first job yet. They hire them to come up with these horoscopes, and they're trained to write them very generally so anyone could latch on to something in them. Something in them matches something in their day if you really want to believe it does. Now, back in the day, astrology was done by the professional astronomers. There weren't very many professional astronomers. They worked for kings and dukes and nobility, and they were hired not to do astronomy per se, but to do horoscopes and astrology for the rulers. And a lot of them didn't believe it. I imagine some of them did believe it. A lot of them didn't believe that stuff, but hey, it was a paycheck, and they could do their astronomy and then write out some horoscopes for the rulers, and so it worked out okay. All right, that's that. And I gotta ask, how many of you have either given or received the pickup line, "What's your sign"? How common is that still? Silence. No one wants to admit that they used it. Yeah. The last class was very vocal about it, so apparently it's still a big icebreaker. Anyway, okay, so that is astronomical time. We've thrown the sun in here. The other big thing to talk about with the sun is the seasons. So let's just set that up in the 8 minutes that we have left. And if there's one thing I really want you to remember from this course, I want you to remember everything for the exams, but long after this course is done, if there's one thing I want you to remember, I want you to remember why it's hotter in summer and colder in winter, because many people don't. And there's this famous video of people graduating from Harvard. On their graduation day, they're asking them this and they get it wrong. And then they go down to the middle school down the street and ask them, and they're doing slightly better than the Harvard graduates. Anyway, there are two answers, a correct answer and incorrect. Shout out both of them. Why is it hotter in summer and colder?
Precession.
Not precession. We will get to precession. That's a more subtle motion.
Isn't it the way the sun hits?
Oblong orbit of the sun.
The tilt of the axis.
Yeah, the
Tilt
tilt
of
of
the
the
earth.
axis.
I've heard both now. I've heard both. Tilt of the axis, and that it's a trickier concept, but that's the correct one. And the other explanation that people latch onto, it's a natural one to think. If this is what you think, don't be ashamed. It's a natural idea, is that the orbit isn't perfectly circular, and sometimes we're closer to the sun and sometimes farther away. When we're closer to the sun, it'd be hotter, and when you're farther away, it'd be colder. And that's true for some planets. Some planets, the orbit is a little oblong, and so there is a temperature difference. But Earth's orbit, here it is to scale. The sun and the Earth are not to scale, but the orbit, the shape of the orbit's to scale. Earth's orbit is almost perfectly circular. We're never really any closer or any farther away. Technically, we're a smidgen closer in winter in the northern hemisphere. So proximity is not the main effect. And you can also understand that because if it was proximity, if Earth were closer to the sun, it would be hotter everywhere. But we know that if it's summer in the northern hemisphere, what's it in the southern hemisphere? Winter, right? And so it's not a proximity effect. It has to do with the tilt. And so here's a diagram, but I think, you can look at the diagram here, but I'm gonna actually use the webcam and I'll demonstrate it using the globe and a light I've set up. Let me turn this around. Set up something like that, maybe a little bit higher so my head won't be cut off. When I'm talking to you, then I gotta flip, and I actually have to flip again so I get north in the right direction. Okay, let me go over there. So, right, it's all about the tilt. North is to the left. It's tricky for me because I just changed my orientation, so now my north is over there, but it should still be the same place as you're viewing it. And so we're tilted over in this direction. And this is the sun, the ring light's the sun. The table is the planet of the solar system. Here I have the Earth, and you can see Earth is tilted on its axis. And as we mentioned last time, it's because early in our solar system's history, Earth was struck by another planet, maybe about the size of Mars, and tipped it over. It sounds wild, but we're going to see this is actually common in the history of the solar system. All the planets got whacked. Anyway, so we're tipped over a little bit. And the way this works is, we're spinning on our axis, we're rotating. This is counterclockwise as viewed from the top, west to east. And as we're doing that, we're orbiting the sun. But as I orbit, the tilt stays the same in space, at least over the time scale of a year or two. I'm standing over here, so I'm not blocking it. But as I'm going around the sun, the tilt stays stationary. So sometimes, like when we're on this side, our hemisphere, here's the northern hemisphere, here's North Carolina. I'm pointing North Carolina towards the sun, so this is like the middle of the day. We have very direct illumination. And the more, we'll see there are two factors that matter. The directness of the illumination, and here it's pretty direct. The other is the duration of the illumination. And as we come over here, this would be winter in the northern hemisphere. Here's North Carolina again. I'm pointing it as towards the sun as I can. And you can see the illumination is not very direct. It's direct down here in the southern hemisphere. The light is spread out, diluted across the northern hemisphere. So this is indirect illumination. Up north in winter, direct illumination in the south. That's their summer. I come back around here again. We have direct illumination in the north and indirect, less direct illumination in the south. Anyway, I have a lot more to show you with the globe and light demo, but I don't think I have enough time left, and this is all the farther I got with the other class. So I'm going to pause just a couple minutes early and open it up to any questions. Because you've all been very quiet today. The other class is pretty boisterous, so you're going to have to step it up. So questions?
I do have a question on just like a concept, like whenever we do like the math where we cancel out the common like if it's degrees, you cross out the degrees, and if it's hours, you cross out hours and stuff. Can you just like do like a quick tutorial on how to do that? Because I don't really understand.
Yep.
Yeah, I need that too.
Yeah, and this is, for many people, the mathematics is tough. And so, I'm covering the concepts, but I'm also trying to ramp you up on the mathematical tools. And so these are really exercises. It's almost like unit conversion. We're going from one unit, like here's a simple one up top. We're going from hours to minutes. We had a certain number of hours. We want to convert to minutes. We know in 1 hour there are 60 minutes. So in your head, well, if I want to go from hours to minutes, I need to multiply by 60. And that's fine. If you can do it, lickety-split like that, great. For some people, they say, okay, I know the conversion factor is 60. Do I multiply or do I divide? And if you divide it, you'll end up with the wrong answer. And that's what this bracket notation, which is used in chemistry courses a lot, is really good for. So everything up here is in the numerator. These are things that are going to multiply together, and then you divide by each thing in the bottom. Think of them as fractions, like 6 times the fraction 60 over 1. Anyway, I put the brackets there, and as long as you write the units, you can't get it wrong. In fact, I made the mistake myself here. I put it backwards, so I had hour up here, and I had hour up here and degrees down there, and then my hours wouldn't cancel. So that told me, oh, I got the fraction, the conversion backwards. And so I corrected myself. I put the hours down here, degrees up there. Then the hours can cancel. Numerator cancels with denominator. And then I can just multiply across the stuff in the top and divide by each thing in the bottom to get the answer. So it's just, yeah, oh, good. I'm glad I got that vocalized. Oh, because then I know I made some sense there. It's just a way to help you not to make silly mistakes by getting numbers backwards. Often people, when doing these things, they just do the numbers and they don't mess with the units. They figure it's a hassle. But if you put those units in there, it will make sure you don't get it wrong. Other questions?
The hardest thing for me about the bracket notation is I understand how it works, but sometimes it's a struggle for me to figure out when it's necessary to use it.
So, if I give you an equation, it's a little different. If you have an equation, it's plug and chug. If there are certain things in the numerator, you plug those in. Certain things in the denominator, you plug it in. The bracket notation is really good for unit conversion. If you have to go from one unit to another and you have some conversion factor. In this, like here, we had a conversion factor of 4 minutes earlier every day. Sometimes the conversion factors are based on motions, like the Earth spins completely around 360 degrees in 24 hours. It orbits completely around 360 degrees in 12 months. So sometimes it's a physical or geometrical thing that's giving us the conversion. Anyway, it's after 3:30, so I'll let you, anyone who wants to go, you're welcome to go now. And anyone who wants to stick around, I can answer more questions.
Thank you so much.
My pleasure.
Thank you.
Thanks.
Thank you.
Thank you.
Hey, no one said thank you today. I like to record all the thank yous. I just like,
Yep. Well, I'm recording, so I'm getting a handful of them. That's good. I like it. Okay, go ahead. Ask your questions.
I was wondering if you had the Zoom link for the lab section right after this, because I don't think it's on what I got, since I only got it for the section that I'm enrolled in.
So go to the Sakai site. It should be listed there. It's possible the TA did not send it, in which case they will
No, I think like my Sakai page is only for my section. I think there's different Sakai pages for each section.
Oh, I see. You want to go to the other section.
Yeah.
Damn it. What is the other section? The number.
I would like to go to 412, which is starting at 4 today.
412.
Yeah.
Let me see. I should have access to all the different sections. So let me go to my Sakai page. Actually, I have my Sakai page open here. 412. There it is. And announcements, meeting information. So this is by Dylan Dutton. He's my grad student, so he.
I think I have a different TA, so. Okay.
So here.
Let me just write that down. I can see it.
I'll put in the chat.
Okay.
Try to. Come on, give me that. There it is. Oh. Chat, and there it is.
Yeah, I got it. Thank you so much.
Sure.
I have a question about the lab.
Go ahead.
Like, what do I need to do to be prepared for it, or is there anything like I should do before?
Nothing today. Today, they're just going through the syllabus. It's probably only going to last 20 minutes. There are a lot of software tools, and they'll go through the ones that you'll need. You need to get Stellarium downloaded on your machine. They'll walk you through the WebAssign access. They'll tell you about Skynet, though you actually won't get your Skynet account until next week. And then you'll want to read the first week of Lab 1 before going to class, before going to lab next week.
Okay, and is it going to be the same Zoom link that I used for this class?
No, it will be, go to Sakai and your TA will post a link. And that it may be the same link for the whole semester, or they may change it up periodically, but it will be under Sakai.
I don't know if my TA posted a link for mine, which is section 414 later today.
So let's see, 414. Syllabus, there's no link yet. And that's
Yeah,
really,
I'm in the one that starts at 440 as well.
okay, so 1 second. I will email the TA. I'll tell you what, I'll make a note and I'll email the TA as soon as I'm done with the other questions to make sure that information is out there. The TA will realize very quickly that that in this case, she hasn't made the Zoom link, and will send it out promptly right before lab, one way or the other. But I'll email her and ask her to do it right away. Anything else?
Yes, so if we want to go out and sketch the constellations one night, where's like the best place on campus to do that?
You want some place that's fairly dark. I'm not asking you to find a site with a glorious view.
Right.
Probably one of the open courtyards, and don't get too close to the street lights or the safety lights, and you'll see enough. As long as you can find a handful of stars, you'll be able to notice their motion.
Okay, cool. Thank you.
Sure. Anything else? Okay.
Thank you.
Sure.
Wait. Oh no.
Oh, go
Can
ahead.
you hear me? Okay, sorry. My thing wasn't working for a second. So since a sidereal day is technically an actual rotation, like full 360-degree rotation of Earth, doesn't that mean that like a normal solar day is technically like 360.98 degrees?
So, yeah, that's right. So the solar day will be a little bit longer. It will be about 1 degree longer. So we have to rotate on our axis 360.986 degrees to get the sun back in place. Yep.
So when we do that conversion where you essentially get 15 degrees per hour in the rotation, how much does that affect, since that doesn't feel sort of right, since it's sort of inaccurate but not like dangerously inaccurate?
So the difference is with respect to what clock are we using. So the solar clock, it's 360 degrees in one solar day, period, because that's how we define the solar day.
Okay.
Yeah, and so it's 15 degrees per, we rotate on the sky 15 degrees in a sidereal hour. The sun will be 15 degrees in a solar hour.
Okay, that makes more sense, because I was thinking like it sort of added up weird in my head when I thought about it too much. But that's cool. All right, thank you.
Sure, my pleasure.